Uh, Today we will start some work on doing some collision stuff. I'm just gonna look at different stuff in terms of the stream setup here. Yeah, so last time we ended at a place where I did some bounding box calculations and different stuff. Then I did a lot of reading off stream and did some playing around with different stuff. And I ended up with an algorithm that worked pretty nicely, but certainly isn't done yet, as you can see here, for handling uh, collisions. Right now it can't handle multiple collisions, and it has some different issues, but we will fix that as we go along. And there we go. So as you can see, you can jump into a wall. You can adjust how much it bounces whenever you solve the collision. Yeah, so that's the whole idea. A lot of this code will be refactored, and we would probably like a more robust system. I would like to change our bounding boxes, since AABB collisions can be done by checking the center of each box and their half distances to their respective faces, meaning that this is sort of a radius. They can for one, do collision checking by just specifying the center and the half widths of each box. It corresponds directly with the way that we create our rendered debugging visuals. We simply specified the center, and the half widths of each axis, and it also helps a lot in collision detection. Since we can use the center of the bounding volume to calculate the closest point on another bounding volume and calculate the distances between a center of a bounding volume and another bounding volume, both boxes in this instance, and you can calculate how deep the interpenetration is on a specific axis. So yeah. So the center half width algorithm is far easier to work with. That means that we would like to create a second bounding volume. Or rather bounding box. We call it a W center. We can calculate it by multiplying the subtracted max point, the subtraction of the minimum point from the max point, and dividing by 0.5, meaning a division. In vector math, you generally do divisions by one by multiplying with something inversed, meaning that you divide one with whatever you want to divide by, and multiply each part of the vector. So this is basically, we take the half point between the max point and minimum point, and then we simply take the distance along the x-axis, y-axis, and z-axis, and that is our half widths from the center out to the plane, or rather face, of each bounding volume. So we could store this as vectors as before, which I think we will do. And we will call this center and initialize it as actually, I think this, no, since we multiply by transforms, yeah, I think we will do like before. So initialize this as that. Then we will do a vector of well, actually, no, yeah, we do need some half widths, not half widths, but half widths. And we will actually use a vector for that as well. Let's see. These should only be affected by scaling. Anyway, now instead of transforming 2 points, we can actually just transform 1 point. So our overall algorithm will be more robust. So yeah, let's try calculating the new bounding volumes. So we find the appropriate bounding volumes by transforming them. We also want to calculate bounding box. Yeah. So we can actually use the old bounding box type to be calculated from what exactly we did, not inside the renderer, but inside the application up here. We will calculate the center by dividing the distance between, or rather the addition of the minimum and max point and dividing that by 0. The distance is a subtraction instead. Yeah. You move out in terms of the maximum point, and then you walk back in terms of the minimum point, and you get the different axis widths. Let's see. So we want to get the temporary bounding volume and calculate the center here. And we would like to store the half widths as well. And we do the same here. And let's just test that. Yeah, we will also do some restructuring of what we store. So let's do a vector of bounding boxes with width and center, which we will call static, or base bounding boxes as before. Then we will actually create something that we call static bounding boxes, and then dynamic, meaning because this is going to be an optimization, because we will have our base bounding boxes for doing different calculations in terms of I was just thinking about how to scale the widths. Anyway, yeah, I'll get back to that. Anyway, we will, as per usual, store the base bounding boxes. We will be using that to recalculate our actual bounding volumes. We will be placing all scene objects in static bounding boxes, and all characters and so forth in dynamic bounding boxes, so that we can simply do checks between dynamic objects and static objects, and not use the same bounding volumes to do dynamic static comparison checks, but only do interdynamic bounding box checks and so forth. So yeah. Let's see, did I change? Oh yeah, I actually did mess that up. All right. So let's see what we get when we try to recalculate some bounding boxes here. So our first box will have -1, -1, -1, and +1, +1, +1, meaning that the center should be precisely 0, and the half widths should be exactly 1. This is a cubic um, box of yeah, 2 times 2 times 2. Let's see what we end up with here. Yeah, that is the center of, yeah. So we actually do end up with the expected result. Let's see. So that is for our floor, I think, isn't it? No, that's for the test cube. Let's see. All right, this is probably going to be different. So the minimum point is minus 2 and so forth. It's probably going to be 8 on the y-axis. It's going to be 0.5 on the x-axis, and it's going to be 20 on the z-axis, which means that we take half of that and expect that to be our half width. In general, we usually do not need to calculate the center position, but we do it anyway. Let's see, our half widths. Yeah, it works as intended. Let's see, for our next mesh, we end up with the same situation. This is a wall segment. Which is 80 long. Yeah, everything is working as intended. Yeah, actually, you don't need the center position. Let's see. Let's move the object. Next, we want to do the same thing as a as before here. We will simply migrate this method where our current setup will be the actual debugging situation. Let's try center, and let's try multiplying the center point by the matrix and see what we end up with. So our temp, min, and max points. This is probably our floor. Yeah, it gets adjusted so the top edge of the floor is there. Let's see. What does our center get set to? Minus 25. And how does that correspond? Yeah, that actually works. And the half widths. are just the same. We already stored those, so we know that now we have a center of the bounding volume that's placed in -25, and that will 0 point, 0 point minus 0.25, comma 0, and that it will span 80 on the z-axis in total. It will span 40 on the x-axis, and it will span 0.5 on all the other axes. So this means that we now have a different bounding volume. Yeah, we need to check for character objects here. Eventually check for static and dynamic objects and calculate separate bounding volumes. We will do that not in a too long time, in a short while, I should probably say instead. So for now we just use these static bounding boxes and in place that. Yeah, eventually we can simply this is computation wise a bit better, because as you can see we skip one step. We do more pre-calculation when we create the base bounding volumes, since yeah, we could change this algorithm, but what would the point be? No pun intended. Yeah. Anyway, so we create our bounding volumes. These are exactly the same as before. The next thing we need to check is collision checking. I've made these query functions, which I didn't show you last time. This is from a book of about real-time collision detection. So yeah, in part we need to build different methods here. Let's build this instead in a version that checks the min and let's see, the min and half width instead. Let's see, where was the algorithm? Let's see. So let's do, we simply use the same method for now, and call this min max. And then we do some comparisons. Let's see, do we have collision checking, math, intrinsics? Okay. Let's do some include algorithm. Yeah, and of course in collision checking we need the min-max algorithm to be declared. And let's do standard apps. Okay. And we copy this, except we delete the comparisons. Yeah, this needs to be all the volumes when we swap the setup to be separated between dynamic and static volumes, because this -1 is because the player character is stored in the last bounding volume, and I do not want to compare it to itself, then we will have a collision all the time. But we will change that. Whoops. We will change that. Let's see if something return -1, and we will use the of the x coordinate for 1 minus we could do this bitwise, by the way. The player box. Oh yeah, of course we need to have the width and center here. Minus the let's see, I dot center dot, there we go. So if the absolute value is higher than the, let's see, we also need to set that. Then the we could do this vectorized as well. Vectorized and with absolute by stripping the first bit, but we will do that later. Right now we're not interested in doing intrinsics. Let's see, the player center minus the other thing here, player box, half width, and for the x-axis plus the scene bounding box half width for the x-axis. So if the half widths of the two boxes are bigger than the centers, subtracted from each other and absoluted. Yeah, we do not have a collision. And we do that for all the plane, or rather axis. That's before. Let's see. So, does this work? Oh yeah, we are not calling the right method here. Let's see. Let's see. You're supposed to realize that. Bounding boxes. Let's see. You haven't realized that this will work. Wake up, IntelliSense. It doesn't really care. Maybe it's because it's all wrapped in intrinsics. Whoops. I of course do not want to check that. We want to change this. Player check. I didn't change the method here as well. That's why. That's why we didn't realize that my method had changed. So we need to swap that, swap that. It's not IntelliSense that's slow, it's me. I'm sorry, IntelliSense, please forgive me. So right now our object just falls through the whole thing. Let's see. And we do not recalculate the bounding volumes, that is why. So right now it doesn't really get updated. So we need to, we have the collision, we can always get the point. Yeah, we will also have to implement new query methods. So we need to do another of these min max, and we call that min max. Then let's see, game objects, transforms, base volumes, WC, and there we go, bounding volumes. This will also speed up our calculations, which is great. Which is great. Let's see, and we of course have to implement a method that takes in the new bounding volumes. Let's see, and we change that. We simply replace the thing here. And remove that. And there we go. Inside our application here, we do base bounding boxes WC. Yeah, let's do capital lettering here. I know I need to fix this one down here then. There we go. And then we want to pass in the static bounding volumes. There we go. And then instead of doing, yeah, we will still do it, but we will use a different thing here. Let's see. The vector new center is equal to the static boxes let's see center and we will apply a new float temp2 temporarily, which will have new distances, half widths. Let's do like that, and then we use the new center, new center, new center. We will replace all this eventually, like that. All right, everything works. Actually, we're using the new bounding volumes. So this means we can stop rebuilding the old stuff, or rather, start to remove some of the old stuff here. So this is our new thing. And there we go. And we move this to our so-called graveyard. We don't mind storing this for now. Delete the old min-max stuff. We could do that and things will still work here. Or rather not. Let's see. And bounding boxes, let's see. Oh yeah, because we use the bounding boxes right now. Haven't deleted this yet. Okay, let's remove that, and remove that. And down here, whenever we want the center, yeah, this is going to, there we go. Let's see, and we do like that. Yeah, we could, instead of passing it, we could just do like, no, let's just store it in the temporary. And we move this code as well. Down here. We need to fix the next thing here. So yeah. For now we will use this. This will be refactored as well, but we're just trying to delete some of the old stuff here. Oh, whoops. Almost. Somewhere we Oh yeah. Instead of doing that, we want to do, instead of bounding boxes, we want to do, yeah, actually this will not work yet. We need to re-implement that. Let's see. Uh, it will definitely not work, but now we will crash. Uh, we would also like some static bounding boxes to be updated here. Yeah, otherwise, no, that's fine. Um, yeah, static bounding boxes. Uh, so yeah, we also need an method that can get the queries. Let's see. We will just let's see. Uh, yeah, actually our um, algorithms here just need to be modified. Let's see, queries. Let's do a min max and also a min max. Um, yeah, because the half widths are actually containing, let's see, Hmm. Yeah, so basically we want to copy these, call one min max, and set them to that, and then we want this. Wait a minute. Let's just copy the whole signature here, and we want that as well. And we want a WC box instead. Yeah, so basically we're just doing a lot of refactoring. And we're doing it for every axis. The minimum point can be calculated by, let's see, WC. Instead of doing like that, let's comment this out. We do a box center x coordinate, and we do that by subtracting the half width x size. That is the, or rather, let's do it for the index here. So we calculate that, and we do it for the max. So therefore we do a plus, and there we go. Let's see. This is going to be correct. Let's just, for now, we do not need that for testing, as far as I remember right now. Let's see. Oh yeah, we need to fix this anyway. So the minimum point is equal to that. The minimum point is equal to that. The minimum point is equal to that. And the maximum point equal to that. There we go. And now we should have no trouble running our stuff here. Great stuff. We could actually do some distance calculations here, I think. Let's do that. There we go. And we do not draw. Oh yeah, it's because when we do like this, we need to change the application way of doing things. And we actually need to copy this algorithm here. And fix the old one here. We do not need let's see this anymore. Whoops. We do of course want just to change this. Let's see. And we call this sender, and this is distance. There we go. We do still not draw things correctly. It's because we do not create any. We do create one now, but we do not scale it. Oh yeah, so the scaling is not correct actually. What happens if we actually just apply some scaling here? Everything will be whack, right? Yeah. So yeah, the point is fine. We would like for each part of the, let's see, the transform. So inside the transform, the scale is the thing there. So it's the yeah, that's more tricky. I was wondering whether we would want a width height, whatever system. We can do it somewhat brute force here. So the x is equal to the scaling on the transform dot b0 and the first component. Yeah, this is not going to look pretty, but it's going to work. And it's the second column. There we go. Third column. Third thing there. Let's see. For some reason it doesn't. Oh well, I need to recalculate these things anyway. Do I need to do the same thing inside the yeah, I actually think so. Uh, yeah. So it's not less calculations during the actual updating, but it's less back and forth anyway in the overall framework. Let's see. Does that help? We do not have something that it does register correctly, at least. Or rather not. I said that way too early. So let's see. Yeah. Well, that works. So it does seem. Oh, it's because of the double collision stuff then. Let's see. Oh no, it doesn't get scaled properly. Okay. We have a problem here. Um, yeah, the rotation is really screwing with these calculations because we do not want the actual rotations, even though the view projection, or rather the object, gets oriented in that way. Let's see. Yeah, it's because it's 0 when it's not rotated. Let's see, and when we do, yeah, a temporary fix would, yeah, a temporary fix would probably be to add floats to scale X, scale Y, and scale C. Uh, yeah. Scale X, scale Y, scale C, and we just add it like that. Um, this will at least get more readable. Let's see. We do the same thing here. Let's see, I think it's the X one here. No. Since it's rotated, it's still the C, actually. So we multiply this by scale C. Yeah, this is the problem with having column major stuff here. Let's see, and we do like that, we do like that, do like that, and then the scale C here. And then the scale Y. Yeah, there we go. And then the player model. Just set the scale here. We can do then some more simple calculations. Now times the transforms scale x. There we go. Y, C. Get rid of this. And we add that to the collision checking algorithm. Or rather recalculation thingy. Instead of that, we do like that, then like that, then like that. Huh. I did something wrong here. There we go. This is probably better. Alright. Huh? It doesn't get rotated right. I mean, it doesn't get rotated right, of course. Yeah. So yeah, I need to scale these things correctly. I'm gonna assume that they are, well, let's see. Maybe I'm not supposed to, well, this is what actually transforms the visual object. Yeah, this gets complicated because I do not have a specific rotation matrix. Yeah, for rotated objects, this is a problem. Hmm. Yeah, this is actually a problem. This is actually a problem. Let's try that at least for now. Let's not update this and see what we ended up with. Yeah, that didn't work. Now I remember. Uh, yeah. Let's see. Uh, yeah, so you could store the rotation. Oh man. Yeah, so for this to work, we would also like to allocate the float var rot x, meaning the rotation in radians along the x, y, and of course z. And we want to transform, set that to 0. We want to set that to 0 and 0. For these objects that are not rotated, I'm not going to implement them. So for this object, we want the x to be there, and the c to be like that, I think. Meaning that we do minus cosine to the rad rotation, one transform temp rad rotation to x. We do it with sine instead. Here we do it with, let's see, C. We do it with sine positive here. Let's see, we move this down. Let's just move this and copy this, and then copy this, and this, and this, and this. No scaling. Let's see. Will this still work visually? Yeah, it will. So we enable this again and multiply that by the yeah, let's do whatever we do in our translation here. So meaning that the yeah, this is going to need some major adjustments eventually. Yeah, I'll have to figure out a better way to do this. Yeah, maybe whenever we do more complicated object stuff, we we'll update the transform using these values maybe instead, and yeah, we will just calculate a translation matrix afterwards. Yeah, I think this is fine to have at least as separate values for now. We do for the x minus cosine to the rad rotation x well, this is actually a translation of a point. Yeah, I'm not sure this is going to work at all. Yeah, this is not going to work. This is going to look weird. Or at least not totally weird. Let's see what happens if we do like that. Well, it just gets flipped anyway. Let's see, sine. Let's try that. Yeah, so the thing is that yeah, you need to rotate them and scale them. So for instance, this is going to work. No, it's not gonna scale them correctly. Unless maybe, yeah, I need to recalculate the, no. So the bounding volumes, they do not get scaled at all. I mean, if I don't do this, does anything else happen then? Let's see. We have the base walls. The half widths. Do they actually differ? No, they do not differ. Did they get scaled? Let's see, they're almost as broad as the circle in the middle, or rather more broad than the circle in the middle. Now they're less broad, so they do get scaled. Let's see. Let's try cranking this up. No, it doesn't change anything. I mean, let's see, how does our debug visuals get calculated? We take our half widths. and add them, draw them. Let's see. So the floor is still working properly. But yeah, maybe we do want to use the translated minimum and maximum point for the static meshes. We could use that instead. We could simply use the, there we go. So calculate that, create the original bounding box. Instead of doing that, we could then tell our system here that we, and this is somewhat hacky, right? Yeah, this will calculate the correct and translated bounding volumes. Yeah, they will be correct in terms of visuals. The dynamic bounding volume is recalculated. Fine, but we do not have any rotation on the object. Yeah, I think we need to rework this to handle rotations better. Yeah, so for now, as long we don't rotate um, our object, it won't matter. Let's see. Yeah, we might implement something that uses this, so I'll leave it for now. We will do some more cleanup eventually. Yeah. Yeah, we definitely need to redo the transform thingy. But for now, this will do. So yeah, now our collision system doesn't need to recalculate the centers and distances in terms of solving penetrations and uh, different aspects of the whole physics system. Oh well, that was a detour. I didn't expect that I'd stumble upon so much work in terms of doing just that. Let's see. We can actually just replace this by doing like that. And then we could do instead of doing that, we do like that. That looks more neat. Here we want to store it for later. All right. The last thing we would like to do is to, let's see, game object data. And then we would like some part of the creation algorithm here to create a specific bounding box for the game object, or rather the player. Let's see, the player model. I would like not to create one. Let's see what happens. Yeah, we have a crash. Let's see. Let's create a character before we create the bounding volumes. Then we can, for each character, we want to find the we want to create a bounding box like this one. And we of course do the game objects and ask for the character object ID dot mesh. There we go. And we do not need to do that actually, because there we go. And then we ask our application for dynamic uh, and set the game objects character bounding box. Yeah, it will have overlapping ID, but yeah, we know that. Yeah, maybe we need to change that in the future. There we go. All right. Then we have the dynamic bounding boxes. Let's actually disable the bounding boxes here and see where we run into problems. Let's see. Let's not use that for now. Let's do outbounding volumes, transforms, characters, base volumes. Let's see. So right now we don't need the transform. If it ever got rotated, Maybe, I don't know. Yeah, we would need to handle rotation eventually. Let's see. Dynamic bounding boxes. Then we pass in our characters, and for each character, we update the specific bounding box. Let's see. Our dude fell off the screen. Let's see. I'm trying to get it to fly back up. It doesn't work. So somewhere. Object matrix. Let's see. So I changed the bounding volume. Yeah. So now instead of doing like that, we should do like that and play rather yeah, and then we want to play a box instead of that doing the dynamic one here. Let's just take it from the top. Calculate the matrix transforms, that is fine. The physics part of the object, the particle system here. Let's just add this into a scope which is called particles that we close, and then we do something for dynamic objects. We do not, well, plus the size of the dynamic bounding boxes. And then we do the exact same thing for the dynamic boxes for a start. So yeah. Recalculate bounding box. Huh. And let's see. There we go. That is fine. There we go. For some reason, we do create something that is yeah. Uh, maybe uh, yeah. Yeah, this overlaps. So this is problematic. Yeah, this doesn't work anymore. Anyway, because the bounding box IDs can overlap. Plus the static bounding boxes dot size plus that. Yeah, and we of course need to do it for the dynamic bounding boxes as well. There we go. For some reason, a box too many gets created. I think. Looks like the same thing. Oh, well, yeah, of course. Here we need the same thing. Since it's offset into the end of the memory layout. There we go. And now we have our system up and running as before. It doesn't handle rotations, but we will get that eventually. Yeah. Yeah. I'm gonna fiddle around with the recalculation of the bounding boxes at another time. So this section here is for debugging, which means that we can ignore it. Then draw character bounding box. Let me just move these and then repurpose the old thing here. I know this is going to be totally unreadable, but I want to be able to do like that and not store those. And I need to redo that eventually. Yeah. Let's just move that anyway. Let's see, we could do, instead of that, do like this, and then it would work totally fine. Whoops. Nope. There we go. And delete that. For now, we will move it since we will do. There we go. Half widths. Let's see, and then uh, like that, and then meaning that object ID. Replace that. There we go. Now this is a more intact thing that can be moved around so that we don't need to use that then. Okay, so we would like to recalculate bounding boxes. Yeah, that's fine for now. Then we would like a version of a std vector of ints unsigned int, because it will only be verified collisions. There we will player collision. This will be player collisions. Hopefully our naming won't be too confusing. There we go. And we would like a std vector of unsigned ints collisions. Actually, we would rather like a layout that is somewhat different here. We would like to do something like out collisions, meaning that we want to do it more C style, where we pass out the actual collisions. Yeah. Let's see. The collisions, we'll clear them in case they need to be cleared. We could do reserve. Let's just do that. We want to, nah, we do not want to do that. Instead of returning, we would like to emplace the index of whatever. So we calculate the collisions, collect a list of any collisions, and handle that. Now our stuff here won't work. So yeah, we will also need to create some uh, uh, collision resolution. And we won't be using a class as we never really do. We will use a class for the overall physics system whenever I implement something to the like of it. We want the namespace gxe and we want the namespace physics inside both of these files. We want the same headers as in our resolution, or rather checking header. Then we want to build something. Let's see the objects. What do we actually do? We integrate, we add forces. We don't need to modify that for now. We do not need the swap chain renderer or objects. There we go. So yeah, this is going to basically get dumped somewhere inside the collision resolution stuff here. Yeah. So we would like for the system to check for resolutions or collisions, uh, collision detection. Oh, this is also going to go into here. Um, yeah. So we would like a vector of unsigned ints, collisions. Let's actually do a scope here where we do all this stuff so that we do not get any problems in terms of naming later on. Then we would like to address our physics system, check player, check collisions. Well, maybe we should rename it actually. Player check collisions objects. Object check static collisions. Let's call it that instead. And we would like a vector actually here. Dynamic objects, static objects. Yeah, we do some more tight naming here. All right. Then we want to check for const auto reference that dynamic objects in dynamic objects. And then inside that we want to maybe, yeah, yeah, right now we only have one dynamic object. What would we do? Yeah, we actually need something else to handle this. So yeah, let's not pretend we actually do anything that we don't. Dynamic objects. We do only want one, but and we rename that. Yeah, because we haven't actually uh, implemented any more dynamic objects for now, and we will definitely need a different system, or rather maybe just some different logic in terms of handling multiple dynamic objects and their inter-object collisions and all of their interactions with the static objects. So yeah, that will be somewhat different. Yeah, at least. And this is also the static. Yeah, it's actually the static colliders. Yeah, okay. Static objects, colliders, static colliders, static objects. Let's see. Whoops. All right. So instead of player box, we do dynamic object here as well. There we go. Then outside here, we could do const auto reference. Um, uh, um, let's do that. Then we ask our physics system to, let's see, static collision. So we would like our there we go. As one of our references. Let's see. Let's just do the same naming here. Static bounding boxes. And then our collisions. Then we calculate our collisions. Let's try to print it. Size of collisions. Collisions, that size. Yeah, we go from 1 to 0. because the object just drops through the scene. Okay. Then we say if collisions that size, then we want to do something. Let's just check larger than or equal, larger than 0. If it's not larger than 0, and we actually need this outside the scope for now. This is also going to change. Yeah. Okay. We then need some collision resolution. We want something that takes in these things we have done. This is supposed to go inside the thing here. All right. We will break it down into smaller functions. Later on, I think we should try to no, let's just say we would like some information about the contact normal and yeah, the distances that we interpenetrate or penetrate. So let's do a void calculate contact normal and distance we need the bounding box information. Let's do a vector of bounding box WCs. A list, and then do the exact same thing here. B list. And then we would like a vector of G vector out contact normals, and then a vector of floats out distances. There we go. And we would like to implement that. And we do like that. For yeah. Let's just do it. We will expect these two lists to be mirrored. So we would like our out contact normal to place back whatever we get from this. Let's see, resolution. We need checking. And we want the A list I center here, and we want the B list which will be arranged so that we get that. And we also want our out distances to be calculated. Yeah, for now we will do the whole square root thing. And we take the A list center and we take the B list collision index. There we go. And that is what we do. So first, maybe we only want penetration distances out. Maybe we don't want the yeah, maybe we only want that. We could do that instead. Let's see. I'm just gonna add it here. Right now, I'm unsure where to really use it since we do not have penetration resolving functions yet. So right now we calculate that. We do not need that one. Let's just normalize. Let's do like this. So we do subtract the center of the A list here and then the result of this function. And then we normalize that. Yeah, there we go. Let's just add this to the comments so they are in. Oh well, I delete. I'm supposed not to delete it. I actually think. Let's see. We move this outside as well. Yeah. Let's say that we want to start we use a physics object containing the velocity. We do not need these debugging stuff. We need a value for restitution. We again access the physics object here. All right. So this is for each collision. So yeah. Then for collisions, for each collision, we would like to ask the system here to calculate the normal distances and store them. Right now it will only, yeah, this feels weird to do. It won't be like that anyway. So let's just replace it with whatever it does right now. Characters. Let's not signal that we actually do something that we don't. It will just be confusing. We still would like to calculate some information here. Right now we will take these out values here and store them in our scope. Let's see. Contact normals, distances. Then we want to call that I haven't used the resolution header yet. Physics resolution. There we go. Let's see. We do dynamic bounding boxes and we do static. Well, this is a problem. This is a problem. Right now we aren't making a lot of sense. We would like to do it for every pair of so we would like could we do a begin plus colliding index? No, we can't do that. So we can't just pass in the iterator. Ah, okay. This is somewhat stupid. Right now we are not working with extensive lists. We were only working with single objects. Well, maybe we do keep this structure and just do what we intend to do in larger systems, which is to create some I mean well, right now we are trying to do something that is pretty stupid, I think. Let's just do manual work for now. We can always do more uh, advanced algorithms in terms of simultaneous, or rather optimized layouts and so forth. Um, yeah, we need some kind of overall system that um, let's see, that that handles the multiple cases better. Because right now we do not handle it well. Let's see, let's store it in our contact normals and distances. There we go. So for each collision we add some information here. Right now we only have one dynamic object. We will of course have to change the layout, but not as much as we already did. Then we will add a resolve collision vector, and now velocity, and we would like to take in, let's just move this into here where we can see what information we need. We need a we need some character physics object. What do we actually call it? It's physics ID. It's inside the. Is it inside the collision? Checking. No, it's inside the objects, right? Yeah, object. So yeah, we need some objects as well inside our header here. There we go. Need some object reference object. We need a p vector reference dc vector because we're not. Oh, are we gonna change it? No, we're not. Contact normal right now, and we do a float restitution, at least for now, and then Yeah, let's start with that. Whoops. Our dot product is going to be our. There we go. So we calculate the dot product of our projected velocity. Let's see, what should we call it? Let's see. Separating velocity. This will be between static objects, which doesn't move. We do not need to store the velocity. If the separating velocity is below 0, we just, or rather, if it's larger than, or rather, if it's not less than 0, this means that the contact normal of the collision and the velocity of the object are oriented in the same way, meaning that we are having objects that approach each other if the separating velocity is or wait a minute. So the dot product. Yeah, if there are a collision course, we need to correct the velocity. If not, they are separating. So meaning that if it's not less than 0, meaning it's 0 or over 0, means that they are not colliding and or touching yet, or plan to be touching, I think. Or let me just think about this. So we project the object's velocity onto the contact normal, which is pointing in the direction of the collision, which is in this case away from the plane that got collided with. If the dot product is 1, they are the same. If it's lower than 0, they are opposite, meaning that, yeah, so forget what I said. If the dot product is negative, we have something that are pointing in opposite directions. If not, we have something that is either not pointing in either something that is pointing in the same direction, meaning that the objects are separating, or 0, which means that the objects aren't moving in terms of the relatively to each other. All right. So if they are moving away from each other or not moving at all, we do not do anything. We just return. Then we want to calculate a new separating velocity, which is going to be our old one times the restitution, which means how bouncy this correction will be. Then we want to see how much of the velocity is caused by the acceleration. And we also need the time step. Flow duration, I see. So we have the contact normal, we have the duration. Let's see. And we grab the dot product of that. Meaning how much of the acceleration gets projected into the current acceleration, which holds gravity. If it's less than 0, meaning that they are pointing in opposite directions, we correct by already adding in some force to the new separating velocity, which gets our acceleration cost velocity and our restitution. And we check. And I know this is not going to be very fast because of all the branching, but we will do optimization later. We could break it out in different steps. Yeah, I might do that anyway. If it's less than 0, oh, we need a plus here. We want to add that too. If it's less than 0, we want to set it as 0. Sort of clamping it. So this basically takes into account how much the acceleration by the gravity affects the velocity. Let's see. And then we calculate the, let's just move this down. And we calculate the change in velocity. Which is the new separating velocity minus the old one. We need to look at how big our impulse is supposed to be by dividing the change in velocity by the inverse mass of the object. Then we calculate the vector, which is final impulse, which we do like that. And then we add up the information and set the new velocity, the corrected velocity. So we want to, there we go. And let's call this in out. Because we actually do pass in and pass out data through this object here. Yeah, this is not extremely clean and not how I want things eventually, but let's see, resolve collision velocity. Let's do some physics stuff. Then we take our yeah, I need to rename those eventually. Physics ID and let's do let's see our contact normals, right? And our restitution is just going to be 0.5 for now. And our duration is our duration here. Let's see if this compiles. So our object is actually staying in place. Let's see, and we can collide with several different objects, which we couldn't before we did this implementation, meaning that everything seems to be working. We do not solve the penetration depth, but that will come later. We just fix the we just fix the stuff here. Let's do a simple check here if the collision that size is above 0, we do this stuff, otherwise we don't. Uh, So let's see. Reset the renderer. Let's just do whatever here. Let's do a couple of updates here of the visuals. Let's see. If I unlike let's see if let's see we can just do some slow iteration here. If I unlike we do like that. And let's do like this. If there are no collisions, we update the visuals for the character. If the objects are not collided with, we also update the debugging information. Now this looks way more neat than what we actually started with. There we go. Well, it doesn't update that one. For some reason, I don't know what the bug is. I mean, yeah, I made a mistake somewhere. Clear. Let's see. Dynamic bounding boxes. If no collisions, we could set that to green, which is fine. So if we have a collision, well, we of course need to reset the the bounding boxes if we do not have a collision for a frame. There we go. So that's the problem, I think. Well, it doesn't think we have a collision. Well, it's not really good at handling multiple collisions in terms of the debug information, but at least the system works. But yeah, I'll have to solve that bug. So this is the reset. If there are no collisions, we might as well reset everything. Seems fine. This resets everything. Maybe we do not want that. Maybe this is actually bad, because if we have a collision, we do not want to. Huh? Where did it go? Well, what happened? Huh? The collision. We're doing something wrong here. Whoops. I removed the collision resolver. There we go. So now we have indication of, well, yeah, I don't know why I wanted to update that. All right. So if we have no collisions, we clear the debug information, otherwise we do not. Since we already set it up here. Okay, next step is to add position repositioning. And then add a iterative solver. Yeah, but let's see. Now we have no bouncing. Let's see if I get something up really high here. He just smashes into the ground, and I actually think he penetrates the ground a bit. Yeah, he does. So he needs the repositioning to happen afterwards. Well, that's great. I think that will be it for our YouTube part of this series. Hopefully you found it helpful, interesting, or yeah, something else entirely. Feel free to comment, like, or subscribe, or follow on Twitch. Also feel free to support the channel if you want to. Hopefully I'll be seeing you around.